I've looked through an insane amount of Chem 1 practice finals, and I found the same 3 types of questions on every single one of them. So I'm going to teach you how to solve all of these questions to perfection. Question 1 is a molarity question. You'll be asked to find the volume. This question states, how much nitric acid solution in milliliters is needed to titrate 125 milliliters of a calcium hydroxide solution? To answer this question, there are 3 things we need to review: naming compounds and acids, writing the balanced chemical equation, and we'll review the conversion factors needed to plan the overall setup for a molarity question. We'll start with naming compounds and acids. We need to figure out the chemical formulas for calcium hydroxide and nitric acid. Calcium hydroxide is an ionic compound. Recall ionic compounds consist of a metal and a nonmetal. We always balance charges for ionic compounds. The chemical symbol for calcium is Ca, and it has a 2+ charge. Hydroxide is a type of polyatomic ion. It's OH and has a -1 charge. We need both charges to be the same number, which in this case is 2. So we'll double the OH by placing it in parentheses and putting a 2 subscript. Our chemical formula looks like this. Nitric acid is an oxyacid, which is an acid with oxygen. You can either see this as the root name of the element followed by us or -ic. If it ends in us, then the polyatomic ion will end in -ite. And if it ends in -ic, then the polyatomic ion will end in -ate. In this case, our acid ends in -ic, so our polyatomic ion is nitrate. An acid starts with hydrogen. This has a +1 charge. Our charges are already balanced, so this is our chemical formula for nitric acid. Now that we've figured out the chemical formulas, we can write the balanced chemical equation and use these as our reactants. Don't forget, this is an acid-base neutralization reaction, where we have an acid and a base, and it produces salt and water. To figure out the chemical formula for the salt, we combine the inner elements of calcium and nitrate. The metal and positive charge always goes first, followed by the non-metal with the negative charge. Balance the charges by placing nitrate in parentheses and a 2 subscript outside. Our second product is water, and we can see that the hydrogen and the OH form water. Note, this 2 subscript does not come down with the OH. This 2 subscript is only there to balance the charges between calcium and hydroxide. Now we'll balance the entire chemical equation. To balance this faster, we can use the polyatomic ion trick and keep the polyatomic ions together. We only do this when the same polyatomic ions are on both sides. And recall that water can be rewritten as HOH. So we'll count up each element and polyatomic ion. We have hydrogen, nitrate, calcium, and hydroxide on both sides. On the left side, we have 1 hydrogen, 1 nitrate, 1 calcium, and 2 hydroxides. On the right side, we have 1 hydrogen, 2 nitrates, 1 calcium, and 1 hydroxide. To balance the nitrates, we can place a 2 coefficient in front of nitric acid. Since we changed something, let's recount the elements on the left side. We now have 2 hydrogens and 2 nitrates. Calcium and hydroxide stay the same. Now we need to balance the hydrogen and hydroxide. We can do this by placing a 2 coefficient in front of the water. We now have 2 hydrogens and 2 hydroxides, and everything is balanced. We have our balanced chemical equation. We can finally review our conversion factors to plan the setup and get to the math. The 4 conversion factors used in most molarity questions are the metric system. You will typically be switching back and forth between milliliters and liters. So either one of these conversion factors will allow you to do this. The next conversion factor, which is given in the question, is molarity. Since the molarity formula is moles divided by liters, this allows you to convert from moles to liters. Note, whatever number is given as the molarity goes with the moles, and it equals 1 liter. The third conversion factor is a mole-to-mole ratio. This is found using the balanced chemical equation. This allows us to go from moles of one compound to moles of a completely different compound. And the last conversion factor is molar mass. This is found using the periodic table. This allows us to go from grams to moles. If the given question gave you the grams or asked to find grams, then you would use this conversion factor. For our specific example, we will only be using these 3 conversion factors. Let's go back to our question. We're given the molarity of nitric acid, the volume of calcium hydroxide, and the molarity of calcium hydroxide. We're finding the volume in milliliters for nitric acid. Since we use molarity as our conversion factors, and conversion factors go in the middle of our setup, then we know we will start with the given milliliters of calcium hydroxide. We also know we'll end with what we're finding, which are the milliliters of nitric acid. Notice the units for molarity are moles per liter, not milliliter. So the first conversion factor will be the metric system one, which converts milliliters to liters. To convert liters of calcium hydroxide to moles of calcium hydroxide, we'll use the given molarity. Now, since we want our answer to be specifically for nitric acid and not calcium hydroxide, we need to change the compound by using a mole-to-mole ratio. To then convert the moles of nitric acid to liters of nitric acid, we'll use the given molarity. To convert liters of nitric acid to milliliters of nitric acid, we can use the metric system. Our setup looks like this. We start with the given milliliters of calcium hydroxide. Using the metric system, and specifically, 1,000 milliliters is equal to 1 liter, we'll align the same units across from each other and place the liter on top. The milliliters cancel out, and we are now at liters of calcium hydroxide. We're going to moles of calcium hydroxide, so we'll use the given molarity. Place the same units across from each other so they can cancel out, and our moles of calcium hydroxide go on top. We now will change the compound by using a mole-to-mole ratio, which is found using the coefficients in our balanced chemical equation. We know the moles of calcium hydroxide go on the bottom since we always align the same units across from each other. And the moles of nitric acid will go on top. There are 2 moles of nitric acid for every 1 mole of calcium hydroxide. The moles of calcium hydroxide cancel out, and we'll use the molarity of nitric acid next. Place the same unit of moles of nitric acid on the bottom, and the liters of nitric acid go on top. These cancel out, and we'll use the metric system again to get to milliliters of nitric acid. To avoid calculator mistakes, multiply the top numbers separately and the bottom numbers separately. Divide, and we get 100.0 milliliters of nitric acid as our answer. Don't forget about sig figs. The least number of sig figs found in this question was 4. Question 2 is a Lewis structure question. You may be asked to find a combination or all of these parts. We'll do this for each one of these structures. When drawing Lewis structures, we always start with calculating the total number of valence electrons. Sulfur, which is here, has 6 valence electrons, and fluorine has 7 valence electrons. Since there are 4 fluorines, we'll multiply 7 times 4 to get 28, then add 6 to get 34 valence electrons. Next step is to choose a central atom. Since there's only one sulfur, this is our central atom, and it's surrounded by 4 fluorines. Next, we'll place a bond between each element and make sure the number of electrons add up to 34. So far, we have 8 electrons since each bond consists of 2 electrons. We'll place 3 lone pairs for each fluorine. This accounts for the 7 valence electrons fluorine has. We currently only have 32 electrons. We need 2 more. We can't add any more electrons to fluorine since it could only have 7, so we'll place a lone pair on the central atom. Sulfur now has 6 valence electrons. If you were only asked to draw the Lewis structure, this would be your answer. But if you were asked to draw this according to its geometry, the structure would look like this. Which brings us to part B, determining the electron geometry. Recall that an electron group refers to either a bond or a lone pair. We have 4 bonds plus 1 lone pair, so we have 5 electron groups. Our electron geometry is trigonal bipyramidal. Using our electron geometry, we can now determine the molecular geometry. Trigonal bipyramidal is here, and we have 1 lone pair on the central atom, so our molecular geometry is either sawhorse or seesaw. This is our answer for part B. Part C is polarity. The 3 factors used to determine the polarity of a structure are symmetry, electronegativity, and lone pairs on the central atom. When there are lone pairs on the central atom, the structure is typically polar. Our answer here is polar. Part D, hybridization. We need the electron geometry to figure this out. The hybridization of the central atom is sp3d. Part E, sigma and pi bonds. Recall a single bond consists of 1 sigma bond. So since there are 4 single bonds, we only have 4 sigma bonds. Let's draw another structure. We'll start with calculating the total number of valence electrons. Nitrogen has 5 valence electrons, and fluorine has 7. We'll account for the 2 nitrogens and 2 fluorines, so we have a total of 24 valence electrons. Next step is to choose a central atom. Our 2 nitrogens will be our central atoms, and we will place a fluorine on each side. Place a bond between each element and make sure the number of electrons add up. There are 3 lone pairs on each fluorine. There are 7 valence electrons on each fluorine, so that's set. So far, we have 18 electrons and we need 24. So we can place 2 lone pairs here and 1 lone pair here. But we aren't done yet. Though we have the correct number of electrons, this nitrogen isn't happy. Each nitrogen wants 5 valence electrons, and this one has 6. So we can move this lone pair and make this a double bond. This is the correct Lewis structure. For part B, we can just look at one of the central atoms to figure out the electron geometry. Note, double and triple bonds only count as 1 electron group. That being said, we have 1, 2, 3 electron groups, making the electron geometry trigonal planar. We'll now find the molecular geometry using the electron geometry we found, and since there is 1 lone pair on the central atom, our molecular geometry is bent. This is our answer for part B. Part C is polarity. Though there are lone pairs on the central atom, that isn't the main factor we are looking at. The main factor here is symmetry. Since there's an equal pool of electrons, no dipole moment is found, making this nonpolar. Part D is hybridization. To find this, we will use the electron geometry we previously found, and our hybridization is sp2. For part E, we know that each single bond has one sigma bond, and the double bond consists of one sigma and one pi bond. We have a total of 3 sigma bonds and 1 pi bond. Let's draw one more structure, and you know the drill. Start with calculating the total number of valence electrons. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. Add 4 plus 3 times 6, and don't forget to add these 2 additional electrons. Recall that when there is a negative charge, we add those electrons to the total number of valence electrons. So we have a total of 24 valence electrons. Our central atom is carbon, and we'll place each oxygen around the carbon. Next, place a bond between each element and make sure the number of electrons add up. There are 3 lone pairs on each oxygen. We have a total of 24 valence electrons. Now, it seems like this is the right structure, but it's not, because carbon has an incomplete octet. Recall that carbon needs to obey the octet rule and have 8 electrons surrounding it. So we can move one lone pair from any one of these oxygens, I'll choose this one, and form a double bond. A great way to check if you drew the correct structure is by finding the formal charges of each element. Our formal charge formula consists of the typical valence electrons of that element minus the bonding electrons, which are the electrons that are touching that element within a bond, and individual lone pairs, which is really like counting each loose electron on that element. Let's use this formula for carbon first. Carbon typically has 4 valence electrons. Our bonding electrons are the electrons directly touching carbon in each bond, so we have 4 bonding electrons. There are no lone pairs on carbon, so this is 0. We get 0 as our formal charge for carbon. Moving on to the oxygen with the double bond. Oxygen typically has 6 valence electrons. We have 1, 2 bonding electrons and 1, 2, 3, 4 individual lone pairs. Our formal charge for this oxygen is 0. We'll find the formal charge for the oxygen with the single bond. Oxygen has 6 valence electrons. There's only 1 bonding electron, and there are 2, 4, 6 individual lone pairs. This gives us a -1 formal charge for each oxygen with the single bond. All formal charges will add up to the total charge of the compound. We know we drew this structure correctly if the central atom is 0 and the most electronegative atom is negative. Last thing to do is to place this in brackets and place the charge on the outside. This is the correct Lewis structure. Now that we know our structure, we can find the electron geometry. Recall this double bond only counts as 1 electron group. So we have 1, 2, 3 electron groups, making this trigonal planar. The molecular geometry would be the same since there are no lone pairs on the central atom. Both our geometries are trigonal planar. Part C is polarity. The main factor here is symmetry. This structure is symmetrical, so it has an equal pool of electrons, so there is no dipole moment, making this nonpolar. Part D is hybridization. Since our electron geometry was trigonal planar, our hybridization is sp2. For part E, we know that each single bond has 1 sigma bond, and the double bond consists of 1 sigma and 1 pi bond. We have a total of 3 sigma bonds and 1 pi bond. And the third question is on periodic trends. You'll be asked to either arrange elements in order of increasing or decreasing ionization energy. Or you'll be asked in order of increasing or decreasing atomic radius. We'll do 2 different questions on increasing ionization energy and increasing atomic radius. Our first question asks us to arrange the following elements in order of increasing first ionization energy. Recall that the trend for ionization energy is that it increases as we move from left to right across the periodic table, and the ionization energy increases as we move up a group. To answer this question, let's start with finding all of the given elements on the periodic table. Neon is up here, argon is right below it, nitrogen is here, oxygen is next to it, arsenic is here, and calcium is all the way over here. Since we are arranging these elements in order of increasing ionization energy, this means this goes from lowest to highest. So the element with the lowest ionization energy is calcium. The second lowest is arsenic. Beware of this next part. You would think that nitrogen has a lower ionization energy compared to oxygen, but recall there are exceptions to the ionization energy trend. Elements in group 3A are lower than elements in group 2A. Same concept for groups 5A and 6A. Since we are comparing nitrogen to oxygen, this is why oxygen has a lower ionization energy than nitrogen. So this is our order thus far. The elements that follow and have a higher ionization energy are argon, then neon. This is the correct answer. Our second question asks us to arrange the following elements in order of increasing atomic radius. Recall that the trend for atomic radius is that it increases as we move from right to left across the periodic table and increases as we move down a group. To answer this question, let's start with finding all of the given elements on the periodic table. Boron is here, calcium is on this side, gallium is over here, and cesium is down here. We again are arranging this in increasing order, so we are going from lowest to highest. The element with the lowest atomic radius is boron, then gallium is next, calcium is the second highest, and cesium is the highest. This is the correct answer. Here's a ritual that I used to do before every exam that I was a little bit nervous about. Repeat after me. I am capable. I am smart enough. I will do well on my final exam. Now believe it. And to help you achieve it, I created a free final exam review guide to give you that extra push. So make sure to download it. And remember, you got this.